So now that we've finished discussing concurrency as a concept and some of the mechanisms that Java provides to support concurrent programming, it's time to turn our attention to the focus of this course, which is parallel programming. And we'll start out in a mirror way to our concurrency discussion by describing key parallel programming concepts. And then we'll talk about when to apply parallelism, because it turns out that you shouldn't always try to apply parallelism. In fact, there's particular circumstances under which you should apply parallelism, and if those circumstances don't apply, don't bother trying to do it. So what is parallelism? Well, parallelism is a form of computing that performs several steps on multiple processors or multiple processor cores. I'm going to be focusing here pretty much exclusively on multiple processor cores because that's the modern way of doing things. But be aware, if you go back in time, if you're transported back in a time machine, there was a time, several decades ago when multiple processors were the order of business, not multiple processor cores. Same basic ideas apply. So the process that you do, the steps that you involve, there are three of them: split, apply, and combine. The split phase takes a big task, an overall task with lots of elements and lots of work to be done, and splits it or partitions it up into a bunch of subtasks. And it does that by forking, and we'll talk more about forking later. Ideally, the tasks that are split from the big task, the subtasks, are split evenly and split efficiently. So this works particularly well when you have things like fixed-sized data structures implemented as arrays or array lists, because they split very easily and quickly, and they split very evenly. So those are good things to have as your task elements. The next phase, once you've split everything up into their little chunks, is to apply operations to perform the processing on each of the different chunks or the subtasks. So these different subtasks can all run in parallel on the underlying processor cores. Now, what's interesting about this is any given subtask will run sequentially. It'll run on one core to do its thing. But the set of the subtasks will all run in parallel because they'll all be mapped onto the different processor cores. And if you've done things properly, the partitions are done in a way where there's no dependencies between partitions or across partitions. So each subtask can run in isolation. And that's what's sometimes called embarrassingly parallel processing, which is kind of a funny term. And I'll talk more about that term later. When you hear the word embarrassingly parallel, the word embarrassing here is like the phrase embarrassment of riches, where you have so many things that it's embarrassing. Again, it's sort of an idiomatic English phrase. And for those of you who may not be familiar with that term, embarrassment of riches, it may not make any sense, but we'll talk more about that later. So these various subtasks can all run in parallel, although each subtask executes sequentially. And I like to think of this kind of like if you ever play the video game Pac-Man, you have the little Pac-Man running around and things are chasing it. And whenever it gets to a certain point, whenever it eats enough fruit, it can then go and eat all the various things chasing it. And it does those sequentially. There's just one thing that's eating the ghosts. The third and final phase in the split, apply, combine paradigm is the combine phase. And that involves merging the sub-results from all the subtasks that all just ran in parallel into a single so-called reduced result. And this is typically done under the hood by something called joining. So we do forking to partition or to split, and then we go ahead and we do joining to merge or combine the sub-results from subtasks into a single reduced result. And that's essentially the model of parallel computing that we're going to be talking about. There's other forms of parallel computing. This is the one we're going to focus on. And this is sometimes called the SIMD model, because you typically have single instruction, which is the task to perform, that gets performed on multiple data elements. So SIMD stands for single instruction, multiple data elements. A key goal of parallel processing is to efficiently partition tasks into these subtasks and efficiently combine them back together again when we're done. If we can't efficiently split and efficiently combine, then oftentimes there's no real benefit from doing parallel processing at all. We're just spending all of our time splitting things up and recombining them. You can therefore view parallelism as an optimization intended to improve the overall performance of the system. And there's this great article that's shown in the link at the bottom of this page that talks about this whole concept of parallel computing as an optimization to make things work better. And the things we're typically trying to optimize from a performance point of view include throughput, scalability, and latency. And these are three sort of different dimensions of performance. So throughput really says how much data can you get done, or how much processing can you get done in a particular unit of time, like in an hour or a minute or a millisecond. Scalability says as the workload grows, can we continue to have more resources brought to bear in order to handle that workload without collapsing under overload conditions. So scalability typically works by being able to bring more cores to the party to do more processing in parallel. And then latency really has to do with what's the delay in starting the work and finishing the work. So they're all related to each other, but they're distinct concepts. And the goal is to make things be optimized and run as fast as possible. And that's why we have the famous goes to 11 idiom, or go to 11 reference here from the movie This Is Spinal Tap, which is just an absolutely fantastically funny mockumentary that makes fun of heavy metal hair bands. And it's got this great recurring theme of up to 11 that goes on in there. So now that I've kind of given you an overview of the parallelism model we're going to be focusing on here, let's talk about the circumstances under which you should apply parallelism, and by extension, when you should not try to apply parallelism. It turns out that parallelism works best under certain conditions. Condition number one, and this is very important, if the tasks are truly independent. And this comes back to that concept of embarrassingly parallel, which you can read about at the link at the bottom of the slide. An embarrassingly parallel task or set of tasks have little or no dependencies or need for communication between the tasks, and there's no need to share the results between them until everything's done. So when everything's done, the results get merged back together. The sub-results from the subtask get merged back to a single final reduced result. But while the computations are taking place, there's no need for any other interaction. And a great metaphor for this, which many of you have probably done in the past, I know I did when I was in college, you end up not doing your laundry for a while, and you end up with a whole bunch of bags of laundry, and then you go to the laundromat, or you go to the laundry room down the hall in your dorm or wherever you live, and you stuff your clothes into 8 washers at the same time. And that's a classic example of embarrassingly parallel processing, because there's no need for the load of laundry in one washer to have to know anything about the load of laundry in another washer. They all start up roughly at the same time, probably all finish roughly at the same time, and you can do a lot of parallel computation if you can get enough washers to run everything in parallel. So that whenever you think about embarrassingly parallel and task independence, think about doing your laundry in a number of machines at the same time. That's also a nice example of single instruction, multiple data. The data there is your clothes, and the instruction is wash your clothes. So single instruction, wash your clothes, multiple data, different loads of laundry. Another set of conditions under which parallelism works well is when there's lots of data and lots of processing to perform. So if you have a large n, where n is the number of elements in your tasks to do, or your tasks to do, and you've got a lot of work to do to process those tasks, you're going to get a bigger win out of parallelism. Here's a little diagram that graphs the relationships here to make this point more intuitive. So this is something called the N times Q model, and that was a model that was proposed by Brian Getz, who's one of the chief software architects for Java. And in this model, N is the number of data elements to process, and Q is a quantification of how CPU intensive the processing is. So where if N is high, lots of elements, and Q is high, lots of processing, that's the ideal conditions under which parallel processing is going to be beneficial. If N is low and Q is low, you're probably not going to get much of a win from parallel processing. And then anywhere in between, if n is high and q is low, or q is high and n is low, you may or may not get a win. And so you can read the link at the bottom of the page for some more tips on how to figure out what the appropriate value for n times q should be to use parallel processing. Something else that's very important to make things work effectively is you don't want the threads to block, and you don't want the threads to have to share mutable state. That would, of course, start implying some type of interdependency. If you're sharing the mutable state, tasks aren't truly independent. Likewise, if you end up having to block, that may cause some other problems. This is not the end of the world. There are ways of being able to do perfectly nice parallel programs that do a little blocking and do a little sharing. But if you can minimize blocking and sharing, you're going to get better overall results from parallel processing. And because of this, because we want to eliminate or reduce blocking, we want to eliminate or reduce sharing, Java and the fork join framework we're going to talk about later, which is the underlying environment for doing the parallel computations for parallel streams and the Java fork join pool and so on. I'm sorry, the Java completable futures framework. They focus on fork join and work stealing. These concepts may not make much sense yet. I put links at the bottom of the slide if you want to read ahead, but we'll cover these topics in great detail later. I won't hold you responsible for knowing about them till we cover them in more detail, but that's how Java tries to get high parallel processing performance through work stealing and the fork join pool. And then, of course, it almost goes without saying, but I'll just say it for completeness, you're going to get better results from parallelism if you have lots of processor cores or processors. And if you only have one, well, probably not going to get a big win. You might get no win at all. If you have many and all these other factors and conditions hold, you're going to get a win. So that was a quick overview of parallel programming concepts. Obviously, what we're going to do next is talk about the various frameworks that Java provides in order to support those concepts efficiently and scalably and low latency and high throughput and all those other ways of optimizing performance.